Thank you to still be here. But of course, we're going to speak about the serious stuff. So the engine of plate tectonics, mantle convection. And, and what I'm going to do is to simplify things. I'll take the view of the physicist. As Jason Morgan yesterday said, we're trying to provide a framework to predict and to interpret the observation. So first, we do the experiment or the theory or the numerical simulation, and then we can, in this framework, try to interpret the data. So it's going back and forth between all the data, all the observation that we've been seeing those last 2 days, and the physics of convection. But so why do we want to predict, in a way? Well, first of all, we are interested in what are the necessary conditions for thermal convection to produce plate tectonics. Because if we look at the solar system, we're the only planet right now with plate tectonics. Venus may have episodic resurfacing, and Mars doesn't, just is in a stagnant type of convection. So what is the condition that produce plate tectonics for us? Then how can we explain the structure of convection? We've seen that there is slabs, we have plumes, and so how does it organize itself in the planet? Can we say anything about the evolution of the planet from its formation to now? And then we can go beyond and then try to use our knowledge to look for exoplanet or to explain exoplanet when we'll have any data about it. So the observation I'm going to keep from all we've seen is that seismic tomography is showing that ridges are shallow features, and the blue cold slabs are traceable almost at all depths, and especially down to the core-mantle boundaries, even if they wander around in between the surface and the core-mantle boundary. So when we look at any of the tomographic model, I've got the impression that those slabs are delimiting two main boxes. And within those two boxes, we've got those large low velocity provinces, the LLSVPs. Then from the geochemistry, we know that indeed the signature of mid-ocean ridges is quite different from the one at hotspot, and that the hotspot shows the existence of long-lived reservoirs because they contain primitive material, but also because they can get back to the surface recycled crust that have been stored for billions of years. So indeed, in the mantle, we have densities, heterogeneities as well. So then we have the hotspot zoo. So Barbara told us about what we used to call the primary plumes, so a nice big head that would be responsible for the traps, and then the conduit that would be responsible for the long track like Hawaii. And if we look at where right now those long tracks hotspot in the Pacific, for example, are located, well, they are located around the LLSVP, on the edges. And it's the same for the long track hotspot in the Atlantic. If we look back in time, in fact, for the last 300 million years, apparently all the big lips, or most of them, have been erupted at locations that are on the edges, again, of the LLSVP of present-day tomographic images. But it's not the only one, so those primary hotspots. Barbara told us also, we have a number, and actually the most numerous volcanic tracks that we see on the ocean seafloors are short tracks that we can follow between 10 and 40 million years. And for example, one good example is the Polynesia here. And if we look at this Polynesian location, actually 100 million years ago, the Darwin rise there which is also a concentration, a cluster of tracks, was exactly at this place. So we may have also hotspots that are in cluster, and we may have a recurrence in this kind of cluster hotspot volcanism. So now back to thermal convection. So we have a mantle that is hot because of accretion, and the core is hotter than the mantle. And then we have a large temperature difference between the surface and the mantle. So in fact, the Earth is heating the universe. So it's like your water pan. And so because the evolution of the planet is going to be conditioned by the cooling of the Earth, and so by thermal convection. So from a theoretical point of view, you have to solve the continuity, so the conservation of mass, which says that if something is going down in a finite volume, then there must be something going up as a return flow. And then we have the conservation of momentum. And what is important here is that we have two diffusive phenomena. Sorry, the equation is terrible. The diffusive of momentum, the diffusion of momentum that is due to viscous forces, and the diffusion of temperature. And in fact, if I heat a parcel of fluid, it's going to be lighter, so it wants to rise. But then the viscous forces are going to try to hinder its uplift. And then the plume, for convection to be efficient, the upwelling has to be quicker than the speed at which temperature is diffusing. So in fact, we can, in a nutshell, in the mantle, for the mantle, characterize the convection by the Rayleigh number, which gives you the ratio between the engine of convection, so our buoyancy forces, and what is hindering convection, so viscous forces. Then if I plot as a function of the Rayleigh number and the Prandtl number, which compare those two diffusive problems, so my molten planet, my molten Earth, is beginning here with very high Rayleigh number, even higher than in ocean or atmosphere. It depends on the on the cubic exponent of depth. And then as it cools and solidifies, I end up with a very high Prandtl numbers, so that viscous diffusion is much, much quicker than thermal diffusion, so that as soon as there is absolutely no inertia, as soon as the engine dies, then there is no motion anymore. And then the Rayleigh number now is much more reasonable, around 10 to 7. So this is really good news, this really high Prandtl number, because it means that, experiments have shown that for a Prandtl number above 100, then if it's 100 or if it's infinite, then you can forget about inertia. So that in fact, numerical simulation are going to consider that inertia is 0, Prandtl number infinite, and in the lab, even silicone oil or sugar syrup can be a good analog to the mantle. Well, in this sort of high Rayleigh number, so this is the Rayleigh number, and now, so it depends on the viscosity here, and on the temperature difference, the gravity, thermal expansion. So we can plot the Rayleigh number as a function of depth and viscosity of the mantle. So we're going to have convection if Rayleigh number is above about 1,000, and it's going to be first cellular. So it's like if I had really big cells in my mantle. Then for Rayleigh number greater than 10 to 6, we are in the plume regime, where this time we have very localized upwelling, and if the viscosity is constant, also downwellings under the form of plumes. So you see that for 3,000 kilometer depth mantle, and the viscosity of even the lower mantle, 10 to 22 Pascal seconds, we are in the plume regime. So it's really not a mystery if we do observe plume. If we are in the upper mantle, actually, since the upper mantle is also less viscous, we should have plume as well. And in fact, the physics of plume is really well understood, and you can predict their duration as a function of the Rayleigh number. And it gives this dependence on 4 decades. So it's quite robust. And actually, you can predict the longevity of those plumes as a function of the viscosity of the mantle. And you see that to have a long track, like 200 million years long track, you need, indeed, a viscosity of the lower mantle of 10 to 22. Then if you want to explain the short track, you need a much lower viscosity that is more like an upper mantle. But in this framework, there is no cold plates and no LLSVPs. So there is an ingredient that we can use. It's that there may be denser reservoirs, so those density heterogeneities are going to interact with convection. And then, I'm really sorry, what is important is this new buoyancy ratio number, which is the density contrast of chemical origin, so denser, divided by the density contrast of thermal origin, which wants to destabilize the system. So here we have plumes. So this is the classical plume, buoyancy ratio 0. And we've introduced some denser orange material at the bottom of the tank here. And you see that as the buoyancy ratio increases, so as the density of my compositionally denser material increases, the plume shape is really changing. And actually, what happens is that we're getting very quickly quite fat plumes. And fat plumes because there is circulation, inner circulation within the plume itself. So as you heat the plume source, the denser material is going to get hot enough to counterbalance its intrinsic chemical buoyancy, and then it's going to rise. But as it rises, it's losing its heat by diffusion, and so when it reaches a level of what we call neutral buoyancy, well, the orange stuff, it's not going to be buoyant anymore, and so it wants to go down. But this part is still hot, so it's still driving an upwelling in the rest of the tank. And so if you can really got piles, like here, only this portion of the orange is going to rise, and then you've got what we call secondary plume developing on top of the pile. This type of upwellings, of instabilities, are extremely time-dependent, as you can imagine. So we can also do a more mantle-like situation where you're heating from below, cooling from above. And this white stuff, it's with fluorescence, so it's again exactly the same, it's denser, and you see that after a while, so here we had downwelling, and we've got piles, but we've got also very strong time dependence. And if you look at this instability here, so it's rising, and as it's rising, it's emptying the bottom. And so we expect the piles shapes to evolve through time. So LLSVP, they're going to evolve through time. The mantle viscosity in the lower mantle is quite high, so it's going to be maybe several hundred of million years, but they're going to evolve through time. So there have been a lot of work, so both experimentally and also a lot numerically, and even in 3D and so on, but we all agree that only with density contrast under 2%, you can have a whole zoology of shape and of time dependence of those hot instabilities. So it's really easy to have several types of plumes, as Barbara was showing, and so you can get really long-lived and quite narrow plumes that are anchored on very dense material. You can have those spires that are beginning to go up, but then they reach their level of neutral buoyancy, and you've got a cluster of secondary plume on top of them. And then and you can have just, as the tomographic image are instant, just the shape of the beginning of the rise, or even a dying plume. There isn't anything down here because the plume is dying in the asthenosphere. It's not fed anymore, but it doesn't mean that it was not coming from deeper below. So we've got scaling laws with the theory, and so you can predict that the spacing of those thermochemical plumes would be 3,000 to 4,000 kilometers at the CMB, with a recurrence time of the order of a couple of 100 million years. So then you can play the game, okay, can I see all those different plumes, but that may be at different stage of their evolution? And in fact, yes, you can, both in the Indo-Atlantic box, but also in the Pacific. So the several different type of plumes, it's just the interaction of convection with a denser reservoir. And if you begin with a stratified bottom of the mantle, it's going to evolve through time if it's not replenished. And so you're going to end up anyway with what we've got today, so a messy type of convection. So, but it's just plumes and convection. We know that if we have plumes going up, we must have also downwellings going down, and that's good news because we have slabs. But how to make a slab? In fact, you need convection with a strongly temperature-dependent viscosity fluid. So this is the viscosity of the mantle as a function of temperature, and we see a really large decrease as the temperature is increasing, and as a result, you're going to have an asymmetry that is going to develop between the hot and the cold material, because the hot material is going to be less viscous, so motion is much easier. And so as nature is quite lazy, it wants to minimize its energy, and so it's going to do a much bigger cold boundary layer, so more buoyancy, to be able to counteract the viscous forces. So you're going to end up with a really small thermal hot boundary layer and a bigger cold boundary layer. And this is going to translate itself as a difference in morphology. So you still have hot plumes with head and tail, but now the cold downwellings are more like finger-like. And there have been also a lot of studies, both numerical, theoretical, and experimental, and you can map the different regime as a function of the viscosity ratio. So I'm taking the viscosity of the cold stuff on the surface divided by the viscosity of the hot CMB material. And if you're doing this, we have, for low viscosity ratio, typically less than 1,000 or 100, then it's just the morphology is changing a little bit, but the rest is quite alike. But if we have a large viscosity ratio, greater than 10⁴, then you're going to have convection under a stagnant lid. So this is a really good way of making a plate. High viscosity ratio, you have the top of your cold boundary layer, which is going to be very viscous, very rigid. This is your plate. The only problem is that this plate is not going to move. So you're going to have convection under a stagnant plate. And then there is an intermediate regime that is quite interesting. It's for viscosity ratio between 1,000 and 10,000 at quite high Rayleigh number. And in this case, so this is an experiment, 10⁷ in Rayleigh number. And here you see, so it's a cross-section, a laser view, and what you're seeing is isotherms that are indicating, so here the upwellings, And here you've got particles and also isotherm with the downwelling. So you see that the downwelling is quite stable, but we have now several upwellings. So there is a downwelling here, here, and then in the middle, several upwellings. And the upwelling that is closer to the downwelling is a lot more long-lived than the one in the middle. So this is reminiscent. So in fact, you have a very strong influence on downwellings, on the plume stability and the generation area. So I would propose that, okay, so we have the cold slab in the mantle, and they're insulating boxes, and in those boxes, you can have the generation of several plumes. And what is really nice is that we see also on the experiment that the plumes that are the closest to the slabs, in fact, their time scale of life is really related to the life of the slab. So in fact, those plumes at the periphery of the boxes are going a lot more long-lived than in the middle. Okay, but now we have, so this thing here, this regime, seems to be quite promising to describe the Earth with slabs coming from plate tectonics, going back down in the mantle, and then several plumes within each box. The only problem is that if I calculate the viscosity ratio with the Earth parameter, I'm here. So I'm really in the stagnant lid. So now what we need to do is to break the lid. But how to do this? So there have been a lot of trial, and mostly numerical. And what you need is really a yield stress. So you need to say, okay, I'm going to have motion in my lithosphere, so breaking the lithosphere, if the local stress is getting bigger than a certain critical value. But then what you need to do is really to kick hard to break your lithosphere. So there have been a number of recipes that have been used, and the main problem is to relate the rheology of a bunch of grain with the effective rheology that you need to put in the models. But in the lab, we can also try to learn from soft matter materials, so from those complex materials. And here, so I've been trying this for the last 30 years. And the only one I found that was interesting, it's a dispersion of nanoparticle of silica in water. And this solution has the property to go from viscous to viscoelastoplastic and brittle when you're drying it from above. So drying it from above, it's like cooling from above. So in this tank, we've just pour our solution and dry it from above. And then we got subduction that is developing. And this time it's subduction that is only one-sided. We can also heat from below, and then we have the superposition of subduction, so it's a side view, so those slabs are coming towards you, and then you can see also particles going up, so we have also plumes. If we look from the top, you still have this subduction, but here, of course, you need to create new skin, and so you've got ridges. And this time, accretion is really localized. If we zoom on the same system with a different setup, we can zoom on the rift, on the accretion process, and we got at the axis the same kind of mechanical instability that we got in the lithosphere, like overlapping spreading center, transform fault, and even microplates. This thing can even induce subduction when a plume, a sufficiently big plume, is coming under the lithosphere. It can rift it, and then you can get really localized subduction on the edges of the plume. So this could explain a number of observations, for example, on Venus, but also maybe on the Caribbean. So you, as a function, I mean, this process of plume-induced subduction is going to depend on the buoyancy of your plate, so old enough, but also on the strength of your plate. You have to be able to break it. So there is only a certain area of parameters that is available. So we see that if we believe this framework, that for the Caribbean to occur on Earth today, it's a really narrow range of parameter, but for Venus, it would be a lot more easy. And then in the Archean, then the Earth is really a lot more like Venus today. And so Francis said that continent formation could have occurred by plume, and this is indeed a mechanism that could work. You first got a plume, and then it generates a lot of subduction, a lot of granitoids, and then you've got your continent. So I think that we have to look into a viscoelastic, elastoplastic lithosphere, which has memory. This is the fluid that we have, and I think that Dave is going to speak a lot about this. So as a conclusion, the first message is really that there is no dichotomy between plate tectonics and mantle convection. The slabs, they are the cold limbs of mantle convection. And so plate tectonic is the signature of this particular regime of convection that we observe on Earth. Mantle convection is strongly time-dependent. And so you're going to replenish the CMB, the slab graveyard, but the asthenosphere can be regarded as a plume graveyard. You've got several types of hotspot and plumes, and because we have density heterogeneities in the mantle. To make a plate, it's easy. Strongly temperature-dependent viscosity. To break a plate, this is really the problem. And we need a lot more work on this. I'm more and more convinced, looking at my small colloids, that a two-phase mixture, either solid or even liquids, mediated by liquids, and memory is really helping, and maybe it is the necessary condition. And then plate tectonics is only one regime out of many. Thank you.